All right, here we go. Thanks everybody for joining us. Welcome to the Link Tech Talks. My name is Colin Chandler, and our co-host is me, Di. We are both Link Frameworks project scientists. I'm at the DiRAC Institute at the University of Washington, and Me's at University of Pittsburgh. Can you hear me okay? Yeah, great. All right. Yeah, so the Link Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community. And the goal is to further enable LSST science. And unlike traditional talks you might hear at a conference or workshop, the tech talks are highlighting the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analyses of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. The recording that you see going on here is also posted to YouTube at a later date. So today's speaker is Leanne Guy, the Associate Director for System Performance and Operations at Rubin Observatory in Chile. Leanne has been with the project since 2018, also leads the data management science team, ensure that Rubin delivers on its myriad science goals. Leanne has previously worked at CERN in particle physics, where she also has a PhD from the University of Melbourne, and has been at the Gaia team in the past as well. Today, though, we're going to be hearing about the Rubin Science Platform, which I'm super excited about. Leanne, I believe that you've indicated you can take questions during the talk, but we also allow for some time for Q&A at the end. So please ask questions in Zoom or in the Link Tech Talk channel, and you can type the questions in the chat or raise your hand. Both are fine. And yeah, a reminder, they're being recorded and later to be posted to YouTube. So there's that. And so with that, Leanne, please take it away.
Thank you, Colin. Thank you for the invitation to give this presentation on the Rubin Science Platform in this Link Tech Forum. I'll just start by sharing my slides.
Looks great.
Looks great. It's in full screen mode.
Yes, it is.
Excellent. Okay, so today I'm going to talk about the Rubin Science Platform and how we're going to be doing science with the LSST, with this science platform. I'll talk about the data preview program, which is some of the early data that we're hosting on the science platform, and the sort of the functionality that exists already, and then the functionality that we can expect between now and the start. I'm going to assume you have a good idea and understanding of what Rubin
recording in progress.
I suddenly got an echo. Okay, I'll keep going. There was just a bad echo then. I don't know if anything else heard. Okay, so Rubin and the LSST, just a very quick one summary slide to highlight the key point that is of interest, that is critical for the Rubin Science Platform and understanding why we're doing what we're doing. So Rubin is a new large aperture wide field ground-based telescope on Cerro Pachón here in Chile. I'm based in Chile now. And its key characteristic is that it has an extremely high étendue, which means it can gather data, it can collect data, it can survey the sky at a much, much faster rate than any other telescope. Its primary mirror is not the largest mirror of any telescope on the planet, but its ability to capture data and image the sky is unprecedented. And so in about a year and a half, late next year, roughly, the 10-year LSST, which is the prime mission of Rubin Observatory, will begin. And the survey, Rubin Observatory, through this survey, will image the entire visible sky roughly once every 3 nights, detecting billions of stars and galaxies, millions of transients, variables. We will have rates of something like 20 terabytes per night, 60 petabytes of images. This is massive. This is an absolutely massive data set. And this is what's key here. How are we going to analyze all this data? Right, the volume of, not just the volume of data, but the complexity of this data as well. The whole, the download your FITS files to your local computer, open them up, analyze them, load them into memory. This just won't work with this data set. If you are able to do that, set the data down to a sufficient amount that you can download it and load it into memory, which means you've probably made a large number of assumptions and possibly cut out a whole lot of new science from your data. So we don't really want to do that anyway. So the technology and methodologies to analyze the data from the LSST also have to evolve to meet the challenge of the observatory. It's not just about building faster networks and having better storage, and a TMA that can slew and settle in 4 seconds. We also have to rethink how we are going to analyze this data. I'm just really including this mostly for reference, but I'll just have a very quick overview. The survey takes sequential 30-second images. We get about 20 terabytes per night. These are processed by the science pipelines to produce data products in 2 categories on roughly 2 different cadences. The prompt, which is this group here of 3, and the data release, which is annual. So the alert stream data, the alerts will come out every 120 seconds. The corresponding database analog products that are measured on the difference images that go into the alert streams, these come out within 24 hours, and the images that are taken are released within 80 hours. Every year, there's a full reprocessing of all the data to produce the annual data releases, and these data products are served up by basically 2 mechanisms. The community brokers, that's where the alerts go to, and they also provide an interface to the prompt data products and to the data releases. And then through Rubin Data Access Centers, so there's the US Data Access Center, and there's a lot of independent data access centers. Most of these will run the Rubin Science Platform, and this is the portal that will allow you to access the prompt data products, the image services, and all the data releases. And this is just a broad overview of the ecosystem of taking data, processing data, and accessing data. And so today we're going to focus just on the Rubin Science Platform. What is it, and how will it enable you to do your science? So the vision for the Rubin Science Platform was written down several years ago, back in about 2016 or 17, I think it was, initially by Mario Juric, David Chiadia, and Gregory Dubois-Felsman, who had this vision of a science platform to enable petascale analysis of the LSST data by bringing the scientists to the data. So no more downloading, no more trying to load things up into memory. And the people to the data, and the data is stored at these very large compute centers that sit behind the science platform and have resources on demand to people. One of the great advantages of this is that it democratizes access to the LSST data products and helps to give a more sort of more equitable access to people, because all you need now is a good internet connection to be able to connect to a data center where the data products are, and there's a science platform, get an account, and then all your compute and analysis and storage is done on that platform, essentially like it's in the cloud. And I'll talk about the cloud deployment in just a minute. So this is another great advantage of this Rubin Science Platform. Not only does it enable next to the data analysis, but it also provides a more equitable playing field to enable a lot more people who previously might not have been able to afford the resources to do this analysis at their own universities or own data centers, or even in their own homes. Some of the key points I've just mentioned, most of these. It also supports user-generated product creation. So you as the scientist will work with the LSST data, create your own data products to do science, and they are federated with the LSST data products to enable in-depth analyses. We are able to integrate with other archives, like the Gaia archive, for example. You'll see, I'll give you an example of how we can use a TAP service to contact the Gaia archive, to do cross-match, to access data from other surveys. It sets up this collaborative research environment that will allow people to dynamically form teams to work together and share data products. And as I've already mentioned, is supported by a lot of back-end computation and resources. Just a few of the design principles around this. The Rubin Science Platform is open source. The software is in GitHub. You can go and access it. And in fact, many of the independent data access centers that work with LSST are installing the Rubin Science Platform at their sites. And this way, no matter which data center you go to, you will see a common interface. Although the backends are not federated, you can't sync from one to the other, you will see an interface and how you would access your data. And analyses in GitHub, you can simply just clone to the different data centers and use GitHub to manage your code. So entirely open source, designed for ease of deployment. We make very strong use of Kubernetes and Docker for orchestration, for deployment. You can create custom containers. So for example, I'll show you that we have the LSST default standard container on the Rubin Science Platform, which contains a lot of software and tools already. But one thing, and we have discussed this with the project already, is that we might, LINCC might want to consider building its own container that can be deployed on the Science Platform, and then users could choose to spin that up if there are any very specific analyses or software that are part of that a collaboration wants or that LINCC wants to use. And so that's also an advantage of using a system like Kubernetes. And another very key aspect is our VO first approach. Where possible, we are adopting IVOA, that's the International Virtual Observatory Alliance, so virtual observatory interfaces where possible. So for example, TAP, you probably know TAP services from other archives, SODA, SIA for image access. I'll show you some more of these later. And so all these VO interfaces that you would use to access the data externally are also used within the science platform to access it internally. So this is a picture of the landing page at the moment. The Rubin Science Platform is real. It exists. It's deployed at the US, so deployed in the cloud, and this is the landing page. Authentication is via CI logon, so many of you have probably seen this before. You can choose to use your institute, you can use GitHub, you can use an org ID. You just pull down here, you set it up and you choose it. You can see that we have links here to the 3 different aspects. There's a 3-aspect design, there's a portal, there's notebooks, and there's APIs. I'm going to go through these in detail right now. We have links here to documentation and to the community forum where you can talk to your colleagues, get help, and ask about the data products. So I'll just say a brief word about how we've deployed this at the moment. We have many deployments actually of the Rubin Science Platform. We've got some working at the Summit here that are supporting commissioning, generally accessible to the public, but to the Rubin community at large, is our deployment of the Science Platform in the cloud. And we've pioneered this, what we call a hybrid model. The data is at Slack, but our users are in the cloud. And this shows you some of the architecture here of the cloud platform. The telescope takes data, it's processed. So this is in Chile. That data goes to Slack. So we have storage at Slack. We have a QServe database at Slack. We have all our processing happens at Slack. And then we have an interface to the cloud platform where we have cloud storage and we have the science platform here spun up in a Kubernetes engine here, which accesses this cloud store and also accesses the data from Slack. So there'll be a lot of data transfers to and from the cloud to serve the user. So all the user analysis is done in cloud, but all our data is stored in one place. And this is another great advantage of this, is that it can help with interoperability, because we are, down the line, people are going to start thinking about joint processing, about cross-matching with other catalogs, and co-hosting of data centers is something that is a problem that we're going to have to deal with in the future. And this model is also meant to try to address that issue. Okay, so before I talk about the components of the platform, a platform is there's no data in it. You can go in and you can see all the functionality, but if there's no data, you're not going to be able to do very much. So let me talk about what data we have hosted in the moment. We have set up in advance of the start of operations, which is in roughly 18 months, late next year, what we call the Rubin Data Preview Program. And the idea of this is to prepare both us and the community to be ready to exploit the LSST data when it arrives. It's going to be a massive fire hose when it comes at you, and most people won't have had the opportunity to work with that volume of data before. And we also want to test our services so that they don't all fall over on day one when we suddenly start putting this data into it. So we have these planned data previews that are slowly ramping up the services that we deploy, the volume of data, the number of users that we use, so that we can find problems, address them well in advance of the start of operations to make us really ready to exploit the LSST data. So we have 3 planned data previews between now and data release 1. The first one, DP0, is complete. We delivered this in July 2023. It contained 3 components: DP1, which was hosting the desk-produced data products with version 19 of the science pipelines; the DP0.2, exactly the same data set, but with reprocessed data with version 23 of the science pipelines, so a lot newer algorithms in there. And then DP0.3 to support solar system, because the solar system data products are quite different to the other data products that will be used for all other forms of science. And so through this, we have been able to provide to the community through these data early examples of all the different products that you can expect to see. What we can't do is cover every type of science. We don't have every type of object that you might detect with LSST represented in Data Preview 0, but we do have instances of all the different types of data products. We currently have about 900 users, and we are slowly ramping up. If you would like to join, please go to dp0.lsst.io, follow the link to delegate resources, and that will show you how to sign up, get an account, and start to work with the data. If you are based in the US or Chile, you have data rights. You don't need to do anything else. If you are not in the US or Chile, there is data rights agreements are being put in place, and we will confirm data rights before you get an account. I can see I'm probably going to have to speed up a little bit. I won't spend too much time on these ones. And this just tells you what the DP0.1 and 2 data set is. It's a few hundred square degrees simulated by desk in this part of the sky.
Allora, una fissa suprema, scusami il termine.
Sorry. And this just shows you the data set here and some of the simulated images. You can find documentation and tutorials showing you how to work with this data set at dp0.lsst.io. As I said before, we don't have examples of all the different types of science objects you might see, but we do have a new source injection package which will allow you to take the DC2, the data preview 0 images in DP1 and DP0.1 and DP0.2 and inject sources that you know the characteristics for into those images and then reprocess them on the science platform yourself. And that way you can maybe start to do some science with around objects that aren't present naturally in DP0. DP0.3, as I said, serves solar system science. We have here a list of catalogs, the source solar system object and source catalogs. We have tutorials. This data preview was put together with a lot of help from the Solar System Science Collaboration. Thank you very much for that. And we're really happy that we're able to serve up these solar system products together with the products for galactic and extragalactic science. Just a note on some of the resources. This is the DP0 website. You can see there's links to delegate resources, DP0.2 and 3. Please go here to find the documentation, and there's lots of notebooks and tutorials. I just want to put a plug in though for the Rubin Science Assemblies. We have started these recently. These are weekly live virtual sessions that focus on learning to use the Rubin Science Platform. So everything I'm going to show you now, you can go to these sessions, you can try it out, you can work with someone. These are hands-on tutorials, Q&A sessions, drop-in sessions. Come along, drop in, bring your questions, get support. The community science team are there to help you. It doesn't matter if you have no experience or lots of experience, they will help you solve your problems and get started. Okay, so this is the portal. I'm now going to go through the 3 different aspects. The portal, we're really excited now to showcase the newly revamped portal. The portal is the interactive environment for exploratory analysis, data discovery, filtering, visualization. You do not require any programming knowledge to use the portal. So if you're not very confident in Python, you're not very confident in ADQL, go and have a look at the portal first. This is an interactive GUI environment that will allow you to explore the data. The IPAC team have just completely revamped this, given it a completely modern look and feel. It's really nice. I've only been playing around with it for a couple of weeks, but I really like how they've redesigned it. There's this little hamburger menu here. You can see all the DP0.2 and catalogs, both images and catalogs that I've just been talking about. And you can also see that they provide you access to different archives as well. So there's a general tap service, and you can use this to connect to other archives and search for data. I'll just give you a couple of examples. This shows image search in the portal. It's using if you look here at DP0.2, you can go to this form here. You can select the type of image you want. So in this example, I've selected 2. This is a process visit image. So it's a single epoch. It's not a coad. It's been through instrument signature removal. It's been through calibration. These are the images that are used to do difference image analysis. So I'm going to choose some PVIs. This tells me the type. So it's called an LSST CalEx, but this is the name in the science pipelines. CalEx is calibrated exposure, otherwise known as process visit image. I'm going to look for images centered around 62 minus 37. This is the center of the DC2 field. And I'm going to choose one particular visit. I just happen to know the number here. This is a visit, and I'm going to choose the Z band as well. You can't see that linked here, but it is. So this just allows you to visually search and click and put in some parameters. You would click search here, and it will bring you up a nice results page that shows you the image, the simulated image. And here it shows you all the So obviously you've got 189, we've got 189 CCDs, so you've got 189 results. If you can see down here, it's the same LSST visit, but the LSST CCD visit ID obviously changes because there's one for every CCD. We have 189 CCDs in the focal plane. And so you can see here all the single visit images, the PVIs laid out for this one particular visit with LSST. And you can't see it now, but this is all very interactive. So for example, you can see highlighted there in orange, this is the image that I've selected here, of that CCD. And you can also do a lot of interactive playing around with the image as well. There's a lot of great tools up in here you can play with. Go along to a science assembly and they will give you a walkthrough on how to do this. Here's another example using catalogs in the portal, tab and ADQL. This is an example where I non-low redshift 1A in the difference image analysis catalog and retrieve all detections from the source to make a time series. So in the same interface again, I give the position, but I just do a search now with a seconds about a position result. And here I'm searching, it's telling me, these are the columns that it's telling me I want to choose, but I've chosen the catalogs up here, the tables that I want here. This tells me it's DC2, this tells me it's the difference image analysis object catalog. So the object is the astrophysical object in the sky itself, whereas sources are in different detections of that same object over time. So there'll be one object, and it tells me that in that region there within 2 arc seconds, there's one object. So I can take that object ID, and if you see here, there's a little button here that says populate and edit ADQL. If you want to start learning ADQL, you can enter parameters here through the GUI, and you'll get ADQL. So this is to learn ADQL. And in this ADQL here, I've put in very explicitly the DIA object I want, and I'm now doing a cross-match source catalogs to try to get all the different detections throughout the course of throughout the course of the DC2 processing. So I can make a light curve. And when I execute this query, it comes up in a results tab in the portal, and I can create a whole series of plots here. You can click on this button here to create plots. You can add a new plot, then you can customize them here. And because I returned a whole number of parameters here, so I've got the right ascension and declination, the midpoint time, so that's the time of the observation. I've converted fluxes to magnitude. I've also converted errors. I've got errors now on the magnitudes. I've also pulled out the seeing. And so here I can take a look. Here's the light curve over time, and I can see the nice light curve of this supernova 1A. And I can also get an idea of what was the seeing like over the time and how did that affect the observations. And then with a few calculations, I can also have a look at the astrometric precision in that field and try to see what that looks like. So there's lots of analyses that you can do without knowing any coding at all. And that's where the portal is really useful for that. Another great thing you can do with the portal is to query external services. And so coming back up here to this top menu, you can see there's a tab. There's a tab for TAP. And if you pull this down, you can see TAP services here of many other archives. You can see there's the DiRAC one. There's here for our DP0. There's MAST, there's NED, there's SIMBAD. So you can go and query all these catalogs within this same GUI and get back data. And so here what I've done is I've connected to the Gaia one because I know that quite well. And I've done a selection here to receive a sample of filtered sources. So here I say brighter than 20.5 within a circular region. And this here is centered about the Large Magellanic Cloud with a search radius of 5 arc minutes. And then I order them. I choose the order. I order by angular separation. So I compute angular separation up here. I order them by angular separation. And so here you see my very large set. I get 21,000 results. And I can plot this in ejaculation. And you can see that I searched for, I searched in a circle with a radius. And so you can see that's the set that has been brought back. So this
Leanne,
is really nice. Yes?
Can I ask you how long that takes to execute, roughly?
It was a couple of seconds, I think. It's not up here. There is actually a bar right at the bottom where it would tell me the time. It came back pretty quickly.
Cool.
It was ordered a few seconds.
Thanks.
Okay, so that's the portal aspect. If anyone has any other questions on the portal, maybe now's a good time to ask it before I move on. No? Okay. Let's have a look now at the notebook aspect. So you've had a little play around in the portal. That's really nice. You've got a bit of, a feel for the data and what it looks like. Now you want to do a lot more sophisticated analysis. And that's what the notebook aspect is for. The notebook aspect is basically a Jupyter Lab. It's a Jupyter Lab session. You can see here, you probably used it before. We have a series of tutorial notebooks here, one of which I've got open. It's called Intermediate TAP Queries. And this one here is about interactive images. So the notebook aspect is meant to enable discovery by bringing the analysis to the data and providing you with a whole lot of tools and services, cutting edge science. So the LSST science pipelines are installed, Anaconda, AstroPy, you can install yourself, you can pip and install packages, you can develop packages, you can use the ADQL interface to get data from any archive, as well as DP0.2. And these all sit at data access centers, obviously, that provide the compute and analysis resources behind the scenes. So here's just a couple of examples of where the community science team has been working really hard recently with DP0.2 and DP0.3 to produce a lot of tutorials. And you can see here's a selection of some of the tutorial notebooks that are automatically deployed in the science platform. When you connect to your account, you can go to this notebooks directory, go to tutorial notebooks, and you will find everything that's available to get you started and start running. And here's just a selection. Here's one using the point spread function analysis for cosmology. Here's one focused around looking at sample identification of difference image analysis objects. Here's a solar system one on searching for trans-Neptunian objects. And here's one on deblender data products. So what does the deblending look like, and what are those data products? In order for you to not necessarily have to run them all yourselves, if you just want to see what these look like, we have rendered tutorial notebooks. We maintain this site, so you can click on this link here and you can see all the plots that are produced, and you can see all the analyses if you just want to go through without running them yourself. Something very important for working with large data that's going to be very important in the LSST era is how do we visualize large data sets? Okay, matplotlib, I'm sure all of us at some point have attempted to load 1 million data points into matplotlib, and we all know what happens. Well, 1 million is not very much when it comes to the LSST era. So not only will it not work on 1 million, but it certainly won't scale to anything beyond that. And so a set of tools that I'm really a big fan of are the HoloViz tools. This is Bokeh, HoloViews, Data Shader, all these tools for doing really large data visualization. They're all in Python, they're all open source, and so they work really well with our model of the science platform plus our Python-based environment. And these are deployed in the science platform for you to use. You don't have to do anything. There's a color diagram, DP0.2. There are 1 million points plotted in here. And you can see the structure in here in this color diagram in the 2 data. And you can also zoom in. We don't do it right now. This is a snapshot, but you can use these tools here to interactively zoom in and have a look at the detailed structure that's part of this. And this is going to be really important for analyzing your data, looking for structure, looking for anomalies, looking for artifacts, trying to do science in a visual way. You can interactively zoom, investigate artifacts, etc. So there's a few tutorials around that, and those tools are deployed there for you to go and play with. Image services is another big one we rolled out recently. We also have images services, not just in the portal, but in the notebooks. Our image cutout service is the one that's there at the moment. So full image services are not yet deployed. They will be coming in a couple of years, but we do have a cutout VOA SOTA standard. So here's an image you can see, and what I've done is I've used the cutout service to look at that region, define and request a detailed cutout of that region in this. And this is actually a GIF, but it looks like it's played through and it won't replay it. But if you go to tutorial notebook 13, a cutout of a science demo where Christina Williams, I think it is, has got lots and lots of cutouts on source, on single visit images of a non-transient object. And it's unfortunate that this doesn't play because she then superimposed them into a GIF. And so you can actually see the object come and go in this nice little movie that she made, all made from image cutouts. And so it's really nice.
Can I ask a question about that? I've had a lot of people ask me sort of if there's any limits on how much this tool can be used. You know, can you do 10,000, 1 million? Is there any scope for that you might be able to share?
Yeah, so we haven't really defined limits yet, but clearly, if somebody's sending queries every few seconds continuously, nonstop, we're going to end up having to throttle them out. That's not efficient. We will look at ways to try to make it efficient to query, to make cutouts so that it's not just always making the same one, throwing it away, making the same. We'll look at sort of efficiency behind the scenes. We don't have any limits at the moment. We have small data sets, but there are going to be some. We just don't really know what they're going to be yet.
Thank you.
And just to note as well that I'm sure many of you have heard of the 80-hour embargo that exists on images. When the single visit images are taken during the survey, be made available for 80 hours, and that will not be able to execute the cutout service on them for 80 hours. So the only images you will get before the 80-hour embargo period is up are the cutouts that come in the alert packet themselves. And so this is going to be challenging because I know that people will look at these cutouts in the alert packet and they'll want to get the region around it and they'll want to get a bigger cutout, but you won't be able to do that for 80 hours. And this is something that's been given to us by the agencies and above, and so we have to implement it. Okay, so let's take a look at the API aspect now. This allows you to programmatically access the data via virtual observatory interfaces, which means you don't have to be logged onto the science platform. You can be logged onto the science platform, and when you call a tap service through the notebook or the portal aspect, it's exactly the same tap service as if you were sitting somewhere else. So if you're let's say you're logged onto the Gaia archive, and the Gaia archive exposes the LSST tap service, then you will be able to query LSST data and have that transferred over to your Gaia archive or your Gaia science platform area. So here's just an example of a piece of code I wrote. This is actually an old piece of code. I should have updated it to use our Rubin tap, but this is using the Gaia tap URL, but it's exactly, you just put the DP0.2 or science platform tap service in here. You use the PyVO, Python Virtual Observatory package. So you import that, you set up a tap service instant, you define your query. This is, I believe, the same query. No, this is a query, this is a Gaia query to select parallax and magnitudes for stars brighter than 20.5 magnitude. It does a circle with a radius, defined radius. So it does that query, you use the tap service to execute a search, and then you get the results back, and you can see I get 21,000 results back, and then those results are in my science platform space or in my, even just my computer at home if I've set up my authentication correctly. They are there, and I can work with those results. So basically the API aspect allows us programmatic access, and it allows us to access the Gaia data from other tools. This is me writing some code on my computer, but this is, many of you might know the TopCat service, which is tools for operations on catalogs and tables, developed by Mark Taylor, who at least was, I think he still is, at Bristol, which is a nice little GUI tool that allows you to do plots and interact with data. So again, VO first strategy. One key thing here is authentication. And I'm going to show you how to do this now. When you log into the science platform, you use CI login, and we know who you are, so you're authenticated. But you can't just then call the tap service and not authenticate to get the data. So there's an authentication process to go through in order to use the API remotely. And there's an example of it here. When you go to the science platform, if you log in, you'll see your username up the top, in the top right here. And there's a little arrow right next. So on the first, just log in because I'm not logged in. So now you can use GitHub. If you click on here and you go to security tokens, you click on this, and you can generate a security token for yourself. And go to this link here. It will tell you all about security tokens and how you use them. You get a security token and you download it. Now, here's an example working with TopCat. So then you go to TopCat, you've got to put in your user and password, and then you can access, once you've authenticated using the security tokens following this example here, then you get access to the table access protocol, and then you'll be able to see our table access. There it is, data.lsst.cloud API tab. You won't be able to use this if you haven't set up the security correctly according to these security tokens. And there's a tutorial here, authenticating from TopCat from outside the science platform. So once you've done that, you can then execute remote queries on the RSP through TopCat, and you can create some nice color magnitude diagrams. Okay, so that's it for the different aspects of the science platform itself. Talk about some of the supporting infrastructure of the science platform and additional functionality that you'll be able to see soon. Does anyone have any questions on those aspects of the portal or any of those examples, or before I go on? No? Okay, I'll move on. So software tools. If there's no software, if your favorite software isn't installed on the science platform, it's going to be a bit useless. You're not going to be able to do very much. So with all software, including the science pipelines themselves, we are fully anticipating that a lot of people will want to use the science pipelines to reprocess data. AstroPy, for example, and many, many other common tools are there that you would use in Python. When you spin up the science platform in the notebook aspect, you can choose the different versions of the platform you want. So if you analyze with an older version, you can. The recommend. We always have a recommended version. Tutorials and examples are all up to date with the recommended version of the science pipelines. So that's choosing the version of the science pipelines that you want. When you get into the notebook aspect, you can come up here. You can select the kernel you want. And here, the default LSST kernel is the science pipelines, AstroPy, Pi, where that we deploy automatically. The Solar System Science Collaboration, for example, had some very specific software to solar system that they wanted to deploy on the science platform, but maybe not everybody wants it, and you don't want to bloat up every kernel. We could then develop an LSST solar system kernel, deploy this, and this would then have the software that very specific software to that science collaboration. Likewise, LINCC as well, I think, has got a lot of tools, so we might want to think about collaborating with LINCC to do something like that. The languages that are supported at the moment are Python and C++. These are the languages that the science pipelines are written in. These are the languages that a large number of software for astronomy are written in. So we think we cover most bases with this. And as I've said already, users can also install their own software. Pip install works really well. Compute capacity. So compute capacity on the science platform is not unlimited. We have this sort of very vague requirement of providing at least 10% of the total data processing capability to our science community. I think that's really a bit vague, and when it was written a long time ago, I think there was more of an idea that the whole field would evolve, and that it might be easier to get compute, or there might be different ways to access compute. So what I can say at the moment is that 10% will certainly not be enough to satisfy the needs of, say, dark energy analyses, let alone all the other science. And with this 10%, we assume that the dark energy science collaboration has DOE provided resources elsewhere. And true, because they have NERSC and they're fully funded. We'll have some sort of transfer mechanism set up for the data products that the dark energy science collaboration want to use for them to be transferred to NERSC. And so most of their users are probably going to work there. The rest of the compute will be spread across most of the other users. And I think that basically we're going to see how that goes, monitor the situation, well, basically see how it goes in operations. We have our cloud-based science platform, but we also have a lot of independent data access centers as well, which we're also hoping are going to contribute a lot of compute to help support the community. The independent data access centers a lot of them are part of the in-kind program. So this is countries other than Chile and the US who are contributing resources in order to have data rights. And so, for example, if you're in the UK, there is a very large data facility in the UK, and they will have all the data products. So you might want to then go and use some of their compute there. And so I think that this is something that we're still looking at how this evolves and understanding this field as we move towards the start of operations, understanding the use cases, understanding the usage patterns. But it's not going to be a case of no science, there's no compute left. We will work to make sure that science can be done.
Leanne, can I preemptively ask a question, which I'm sure other folks are curious about? And I know we've talked about this before, but I think folks are curious about GPU access in these different scenarios.
Yeah,
if you could just say something about that, that'd be great.
Yeah, I think I have it on a slide coming up, but I'll answer it now. It's fine. So the Rubin Science Platform deployed at the USDF and in the cloud does not have any GPUs. It's all CPU, and at least at the moment, we are not able to provide GPUs to our community. The simple reason is that we basically just have to finish building the science platform with the base functionality that we need in order to go live into operations for people to do science. And we just don't really have the resources to dedicate now into being able to support GPUs and to changing that model right now. I'm not saying that'll be the case for the whole duration of the LSST, but at least immediately that's not something that we can really do on project. I do recognize, and so does everyone on project recognize, that increasingly GPUs are becoming important to train machine learned models, and machine learned models are becoming increasingly important and a big part of doing astronomy. So we are very well aware of how the field is growing and the importance of this. And we are trying to work with the independent data access centers to see if they can bring GPUs. So we're hoping, and there's no concrete commitment yet, But that is where we're looking to see if can the independent data access centers help us out by providing some data centers with GPUs where perhaps people could train models, do some of the most intensive tasks that require GPUs there, and perhaps then install trained models on the Rubin Science Platform to then run over the whole large data set. That's our initial approach, but we will continue to evolve with the field as the field evolves.
Thanks. I think this is also a good time to voice Henry Ferguson's question in the chat there. If you have plans for implementing user quotas or CPU and/or data storage once operations start.
Yes, we do. There is a birthright data storage. I believe that we're going with 1 terabyte at the moment to start with. There will be some sort of user type, what did I say here? Time allocation committee. There'll be that's really for user batch sort of. I have it. It's a little bit further on. Yes, we have user storage limits, but there'll be some sort of allocation committee type process, users committee, something like that, whereby if you have a really special need and you want to present that case, we can consider it. There's no promises, but yes, there will be limits. We start out with the terabyte. I believe that's what we're starting out with.
Thank you.
Okay. For how much compute we think we're going to need, how much storage, and clearly here training machine learning classifiers. This is the big one where GPUs comes in, and yeah, computing periodograms is also not cheap as well, and so we're also working with an in-kind contribution team and hoping that we can maybe integrate some of the functionality they deliver into the science platform and maybe look at how we could do that efficiently behind the scenes, not have every single person computing the same periodogram every time. And so there's some work going on in that area.
So then could you just, for those that don't know, could you just give a quick definition of the in-kind so people know what that's about?
In-kind. So if you are based in the US and Chile, this doesn't really concern you because you have data rights. The LSST data is available to everyone who is in the US and Chile, but if you are not part of the US and Chile, then you don't get data for free. So you have to buy into the data. The prompt data products, the alert stream and the prompt data products, these are world public. And so people can work with those early time domain data products, but anything that's part of the data release processing, so coads, for example, deep coads, fully reprocessed years on data, years and years of data on top of each other, on top of it, not just the single visit images. This all falls under data rights. And so I believe it was the agencies that fund LSST wanted to put in place what's called an in-kind program with some of our foreign partners. And so rather than paying for data, just paying an amount of money, they contribute resources or software or people or CPU. And so Data Access Center is a compute and resources to do analysis. And so then there's Aprajita Verma in the UK is our person who does a lot of work in coordinating the in-kind program. She's doing a great job of that. Knut Olsen also works with it as well. And so there's a way that they work out, okay, if you provide X amount of storage and compute, then you get X number of PIs and junior assistants who have access to the data. So these resources are then used for the good of everyone in the Rubin community. And one of the in-kind, there's many types of in-kind contributions. Data access centers is just one of them. Software is another one, helping out with commissioning, directable software engineers who can come and help work with us on short-term projects. So independent data access centers are one kind type contributions that will be available to people throughout the community.
Great. And just to clarify, there aren't data rights needed to go and work with the data previews right now, for example.
Yes, actually, there are. You have to be a data rights holder.
That's why I asked. Thanks.
Yes, yeah. Okay, so user batch. These are, this concerns running in bulk over catalogs and image data. So you want to do a big bulk reprocessing, you want to run the science pipelines, you don't want to do that interactively in a notebook. So we will be putting together some sort of user batch system, which will allocate resources to users in order to do large reprocessings on the science platform. And with time allocations to decide what's equitable and how this is divided up and what is fair. This hasn't really been put in place yet. We only have small amounts of data at the moment. We're not stressing the system, but this will come into play in the next couple of years. One of the big things about the science platform is that it supports collaborative work. So the creation and sharing of data sets. So you log onto your account, you create data sets, you want to share that with your co-authors on a paper that you're working towards and that those products and data products are supporting. So there will be workspaces that will be created that will allow, collaborations or groups of people to dynamically form, work on something with a set of data products and then publish their paper and then go and do something else. And so that will be it's not in place yet, but that will be a nice aspect of the science platform. Our backend services, I probably covered a lot of this already, but this is, I guess, here just for reference. Obviously, we've got database services that sit behind the science platform. So both the prompt and data release catalog data products. We also have user databases, which will be in a relational database. All of these are accessible via ADQL. So that's the astronomical version, essentially, of SQL. You take SQL and you put a lot of astronomical functionality on top of it. File services, so there will be a per user file function. You'll be able to upload code, store selected or transformed subsets, upload data from other surveys if you want to work with it. And then computed data facilities, you'll be able to launch analysis via all the different aspects and access the data from all aspects as well. This just shows you, I don't expect people to read this, but just shows you the success so far of DP0 and the Rubin Science Platform. These were flash talks that were given last year. We had over 50 people from the community who had worked with the DP0. This is just DP1 or 2. This has a similarly at the DP0.3. Use that in order to do some form of science analysis and start to prepare for LSST. And so this was a really nice set of presentations in the range of science that's being done. So just finally, as I wrap up, I want to point you to the Rubin Community Forum. If you have a question, you don't know where to go to the Community Forum. There are many categories here. Basically, the size of Rubin, it's not just the volume of data that's big, it's not just the complexity of data, it's also the size of our community. We are expecting something like also people globally to be working with the and the old forms of help desk, these just aren't going to scale. I mean, you imagine 10 different people send the same question, 100 send the same question to a help desk, you might get an answer. This doesn't work. This is not a model for the 21st century. And so we're building a model for community science around software called Discourse. This was developed by the people who developed Stack Overflow to help build a community that can crowdsource solutions. So it's more like a peer-to-peer network of people. So if somebody has a question about a data product, it doesn't have to be someone on project who answers it. It could be somebody else in the community who's already come across that project and can help out. A lot like on Stack Overflow, which you go to Stack Overflow and you see someone's already asked the question, you can see the answer and you can contribute to it. We hope it's going to be a lot nicer and kinder than Stack Overflow though. Stack Overflow gets a bit rough at times, but we're looking to build a much more friendly, inviting, welcoming platform and discourse. So if you have any questions about Rubin, LSST, the science platform, the data products, come here, ask your question. You can see that lots of people on the project already answer questions and then help out the community. Okay, so I just have 2 slides left, which is good timing, I think. The DP0 era Rubin Science Platform, or the science platform that we have at the moment, this is still under development. And I really want to stress this. It's still under development. It is a prototype version of what's coming, which means that it's not just the full set of functionality that's not available yet. It's also things like the performance. It's not as performant as it's going to be. The current performance doesn't reflect the performance of the final system. All the resources that we have, I mean, what they have now, there's going to be more. There'll be probably larger final quotas. There'll be more processing capability. Bulk download, for example, we don't have that in place yet. That will go in place, but it's only going to be available to data centers. Don't have the full set of images in place yet, so we only have a cutout service. We don't have service in place yet. So it's still under development, so please, bear with us. And if you find issues, please do let us know. Go to the community platform, report these, and help us to build the best platform we can so that when the LSST data comes, we're all ready to do science with it. Some of the things that you can expect coming up in the future are user database tables. We don't have these yet. I've talked a little bit about them so far. You'll be able to take the data that you have selected, stored, subsetted from the LSST data. You'll be able to download it, upload it, join it with other data sets, federate it with the main catalog, do an analysis. Perhaps you want to do some analysis on the data, generate some photometric redshift estimations using a novel photometric estimator code, and then maybe you want to federate that with some of the LSST catalogs, or you want to use Gaia catalogs. Those sorts of user database tables will be there to support those types of analysis in the future. Parallelizing, there will be an initial allocation of CPU time. As we discussed this already, there will be a resource allocation committee for additional quotas if you need them, but these services will be available. This isn't in place yet. Syncing between RSP accounts and personal devices, not in place yet, but we envisage a lot of people are going to want to write code on their laptop, not just log in and work on notebooks, but you want to code on your laptop against a small development set with, using a full IDE, for example. I mean, I like to use PyCharm. Other people like to use Visual Studio or VS Code. So that's coming. Sharing within private groups, we've talked about that, but we don't have that yet. Bulk data download, as I've just said, this is available to data, full set of image services and collaborative analysis. So there's still lots more exciting stuff to come. And we hope to be rolling that out over the course of Data Preview 1 and Data Preview 2. And that's the end of my presentation. I've just listed a set of references here to help you. And I will end there, and I'm happy to take any more questions. Thank you.
Awesome. Thanks so much, Leanne. Yeah, let's open up the floor to questions. And let's see, I saw a raised hand and came back down. But yeah, let's open up the floor to questions. If we've got any, you can type them in chat. You can also raise your hand here if you like, whatever's convenient. Meg, go ahead. Meg, I don't know if you can hear me. Oh, there we go. Meg, I think.
Sorry, I couldn't unmute and was just starting to chat that I can't unmute.
Thank you. Got it.
So great talk. I just wanted to ask a little bit about some of the features that you said are coming. It sounds like those are things you also want feedback for, but I don't get a sense that these are coming soon. Do you have a sense, or can talk a little bit about the schedule for some of these features, like being able to create tables is really, user-generated tables is really important, especially playing with DP 0.3 and things like that, because it's stuff that we would be doing. But it's hard right now because we're not doing that. We're not really simulating what we would do on the RSP right in the future. So just wondering do you have a timeline for when some of these features would be available on what is currently the prototype, or is that these won't be available in the prototype and there will be a quote, one day the RSP will turn over into a different or production version that would have some of these?
No, okay.
If you can just talk a little bit about your plans for rollout of some of these features,
okay.
that would be great.
So one day the RSP will just turn out into a rolled out version. No, that's not building up now. We're going to build up incrementally. There's no stop. That was the prototype. It's gone now. We are incrementally building up the service. And I think at just one point, maybe, I'm not sure technically if we'll say, right, start of operations, here's a set of functionality, we'll tag it version 1. I don't know if we'll do that. Maybe we will, maybe we won't. But we are going to roll these out incrementally. There's not going to be some sort of end the prototype, start the new one. You touched on the example you gave, Meg, was exactly the one that I and we on project think is the most important one, which is user database tables and user tables. We really, really need to be supporting user-generated data products when we start operations. So that's probably our highest priority in all of this. As for an exact timeline as to when they're coming, no, I don't have that. It's probably a good thing to do, and I'll take it back and think about it. At the moment, we're sort of really thinking in terms of what do we need before the start of the survey? What is it that we cannot go live without, and what is going to be nicer to have as we move forwards? So, images, alerts, single visit image going to be some of the earliest data products that come out, right, through the prompt stream. Data release processing isn't going to come for a long time. So let's say, for example, people aren't necessarily going to be doing a full reprocessing of a set of PVIs to look at the background estimation, calculate a different background, and do a different subtraction. That's more of a data release sort of type of analysis. But operations on single visit images, so for example, the cutout service, right? Once an image comes out of embargo, a lot of people are going to want to make cutouts on it. So that's going to be one of the services that I think we need to have fully out there, good performance, well stress tested early on in the survey. So we're sort of looking at what are the early data products, what's going to enable the earliest science, and hence what do we want to put our effort onto. And we're very happy to take your input.
I agree. We've got a couple more hopefully quick questions, but let's see, from Nevin over there in the DiRAC room. Can you tell us if there is any collaboration with Fornax, the NASA platform?
Fornax, the NASA platform. Collaboration in what sense? Do you mean around data, sharing data? Do you mean having co-hosting of data? Do you mean development of science platforms? But on all of these, actually, it's no. So, but I'm curious to know what you were thinking at it from.
They've been saying for development.
Development of science platform.
Okay.
No, it's Fornax is a completely independent science platform.
I think so. A quick question from Henry. Again, there is asking, unclear on how much is there CPU in Google Cloud and the data is at Slack, or some data being mirrored on Google? I think that's the gist of your question. If you want to.
So
one time.
That the interim data facility moving over to Slack. So Slack's our US data facility. It's ramping up. It's close to ready to go. We did have the catalogs in the cloud. We did have images in the cloud. It's all going to be at the USDF. And in fact, we're in the process of moving a lot of that now. So using the TAP service, cloud will query a catalog. Behind the scenes, it's the TAP service that then will query those catalogs, the QServe catalogs at the USDF, and send the result set back. Likewise.
Awesome. Great. Thanks so much.
With what's called client server buckler. So anything that uses TAP, QServe catalogs, that's all out there. It's running with. We're moving all that data to the USDF right now. A new development client server buckler will allow you to do this with the buckler repo and to get images.
Great. All right. Thanks so much, Leanne. That's all the time that we have. Super exciting. Thanks everyone for attending the Tech Talk series today. The next one will be on June 13th at 10 a.m. Pacific. Please join the LINCC Tech Talks channel on Slack, and you can email link at lists.lsst.org for information. And today's Tech Talk will be available on YouTube within a few days. And thanks again very much.
You're welcome. Can I just ask one final question?
Sure.
I see there are a bunch of other questions in the chat. I could try to respond to them, but is there a Slack channel that you would want me to send the answers to?
I think that the LINCC Tech Talks channel on Slack would be ideal. Yeah. Thank you very much for doing that.
I'll take a look through the rest of the chat. I haven't read it yet.
Appreciate it. I think you managed to get through the questions.
Oh, okay.
Thank you.
Great. All right. Thanks very much. Bye, everyone.